Hey everyone, and welcome back to the channel. Have you ever wondered what makes your smartphone so fast and power efficient? Or what's inside the tiny chips that run everything from your smartwatch to massive data centers? A big part of the answer lies in a revolutionary concept called RISC. And today, we're going to demystify it completely. So what exactly is RISC? The acronym stands for Reduced Instruction Set Computer. At its core, RISC is a type of computer processor architecture that focuses on simplicity. Instead of having a huge library of complex commands, a RISC processor uses a small, highly optimized set of instructions. Think of it like this. Instead of a single, complicated tool that tries to do everything, you have a set of simple, specialized tools that are incredibly fast at their specific jobs. We'll come back to this analogy later. To understand why RISC was even invented, we need to take a quick trip back in time. Early processors, now often called CISC or complex instruction set computers, were designed with a different philosophy. The idea was to make the hardware as powerful as possible to bridge the gap between high-level programming languages and the machine code the processor actually understands. This led to processors with hundreds of complex instructions. Some instructions could perform multiple operations at once, like loading data from memory, doing a calculation, and storing the result, all in one go. But this complexity came at a price. These intricate instructions required more complex hardware to decode and execute them. They often took multiple clock cycles to complete, which created bottlenecks. Engineers and researchers, like David Patterson and John Hennessy, noticed something interesting. In reality, most programs were only using a small fraction of these fancy instructions. The majority of the work was being done by a handful of simple, common commands. So the question was, why build these incredibly complex and expensive processors if we're not even using most of their features? This led to a new way of thinking. Let's simplify everything. The goal became faster execution, simpler hardware, and better overall performance and efficiency. This brings us to the design philosophy of RISC, which can be summed up in one word: simplicity. The core principle is that a simpler instruction set allows for a simpler and faster processor. The big goal was to design instructions that could ideally execute in a single clock cycle. This is a huge deal. If every instruction takes just one tick of the processor's clock, you can predict performance much more accurately and push more instructions through the system in less time. To achieve this, the hardware itself was optimized purely for speed, stripping away all the non-essential complexity. So what are the core characteristics that define a RISC processor? First, as the name suggests, it has a small and simple instruction set. We're talking about a few dozen essential instructions, not hundreds. Second, all these instructions have a fixed length, usually 32 bits. This might sound technical, but it makes a massive difference. When every instruction is the same size, the processor can fetch and decode them much more quickly and efficiently, without having to figure out where one instruction ends and the next one begins. Third is the load/store architecture. This is a fundamental concept. In a RISC design, the only instructions that access the computer's main memory are load and store. All other operations, like addition, subtraction, or logical operations, work directly on data held in a small, super-fast memory area right on the processor called registers. This minimizes slow memory access and keeps the processor's core busy with calculations. And that leads to the fourth characteristic: a large number of general-purpose registers. Since all operations happen on registers, you need plenty of them to hold the data you're currently working with. Finally, RISC processors have very few addressing modes. The different ways an instruction can specify the location of its data. Fewer modes mean, you guessed it, simpler hardware and faster decoding. So how does a RISC processor actually execute these simple instructions? It all comes down to a technique called pipelining. Imagine an assembly line for making a car. You have different stations, one for the chassis, one for the engine, one for the body, and so on. While one car is getting its engine, another is getting its chassis, and a third is getting its body painted. You're working on multiple cars at once, in different stages of completion. Pipelining in a processor works the exact same way. The execution of a single instruction is broken down into simple stages. Fetch the instruction, decode it, execute it, and write the result back. Because each instruction is simple and takes one clock cycle per stage, the processor can have multiple instructions in the pipeline simultaneously. As one instruction is being executed, the next one is being decoded, and the one after that is being fetched. This creates a continuous flow of instructions, dramatically increasing the processor's throughput. The simplicity of RISC instructions makes this assembly line run smoothly and incredibly fast. Now, with such simple instructions, you might be wondering, how do you perform complex tasks? That's where the compiler comes in. The compiler is the software that translates human-readable code, like C++ or Python, into the machine instructions the processor understands. In the RISC world, the compiler is given a lot more responsibility. It's the compiler's job to break down complex operations into a sequence of simple RISC instructions. It's like a master-level Tetris player, figuring out the best way to arrange these simple instruction blocks to get the job done efficiently. The compiler handles crucial tasks like instruction scheduling, which is arranging instructions in the optimal order to keep the pipeline full, and register allocation, which is managing the use of the limited registers to avoid slowdowns. The philosophy is do as much work as possible in software at compile time to make the hardware simpler and faster at runtime. So, what are the big advantages of this approach? The most obvious is speed. Simple instructions and deep pipelining lead to much faster execution. Simpler processor design also means they are easier and cheaper to design, test, and manufacture. This also leads to a significant benefit in today's world: lower power consumption. Simpler circuits just don't need as much electricity to run, which is why RISC architectures absolutely dominate the mobile world. Of course, no design is perfect. RISC does have some limitations. Because each instruction does less work, you often need more instructions to accomplish a complex task compared to a CISC processor. This can lead to larger program sizes, which means more memory is needed to store the code. And the performance of a RISC system is heavily reliant on the quality of its compiler. A poorly optimized compiler can generate inefficient code that negates many of the hardware's advantages. Now for the fun part. Where can you find RISC in the real world? The answer is everywhere. The most famous example is ARM. ARM processors are the brains inside virtually every smartphone and tablet on the planet, from iPhones to Android devices. Their incredible efficiency is a direct result of their RISC design. Another classic example is MIPS, which has been widely used in networking equipment like routers and in various embedded systems. The PowerPC architecture, famous for powering Apple's Mac computers for over a decade and gaming consoles like the Xbox 360 and PlayStation 3, is also a RISC design. And more recently, there's a new, exciting player on the scene, RISC-V. It's an open-source RISC architecture, meaning anyone can use it to design their own chips for free. This has led to a massive explosion of innovation in education, research, and the Internet of Things, or IoT. Today, RISC architecture is the undisputed king of mobile and embedded computing. Anything that needs to balance high performance with low power consumption is almost certainly running on a RISC-based chip. This includes your smartphone, your smartwatch, your smart TV, your car's infotainment system, and the countless tiny IoT devices that are making our world more connected. It's also making huge inroads into high-performance computing and data centers, where power efficiency is a massive economic factor. Let's go back to that analogy I mentioned at the start. Imagine you need to build a complex Lego model. A CISC processor is like having a single, giant, custom-made Lego piece that does a whole section of the model at once. It's powerful, but it's slow to make and can only be used for one specific task. A RISC processor is like having a huge box of simple, standard 2x4 Lego bricks. Each brick is simple and quick to place. To build that same complex model, you'll need to use many more of these simple bricks, and you'll need a very good instruction manual, that's the compiler, to tell you how to put them all together. But because each step is so small and fast, you can build the entire model much quicker overall. So, from the supercomputer in your pocket to the invisible chips running our world, the RISC philosophy of simplicity has proven to be one of the most powerful ideas in the history of computing. It's a testament to the idea that sometimes the smartest solution is the simplest one. Thanks for watching. If you found this breakdown of RISC helpful, be sure to hit that like button, subscribe for more tech deep dives, and let me know in the comments what topic you'd like to see covered next. See you in the next one.